Hello everyone and welcome back to tutorial 5 of MIE100, the dynamics course in the University of Toronto. Today we're going to continue our topic of kinetics of particles, but this time we're going to talk about work and energy. I'm going to be doing 3 problems with you to help you understand the content better, and as always, if you have any questions, leave it in the comments below. Okay, so starting with question 1. The 10 kilogram collar slides on the smooth vertical rod and has a velocity v1 of 2 meters per second in position A, where each spring is stretched 0.1 meters. Calculate the velocity v2 of the collar as it passes by point B. Okay, so as usual, we'll first list our known value variables. We've got the mass is 10 kilograms. V1 is 2 meters per second. The extension of the spring is 0.1 meters. This is the stretched part of the spring. The stiffness of the spring is 800 newtons per meter, and we want to find V2. Okay, so we're going to start first by finding X2, which is the stretched part of the spring at B. So how do we do that? We've got the spring here. This is point B. And we know that this distance over here is 0.3 meters. And this distance over here is 0.4 meters. That means we can know what this length is, L2, the length of the stretched spring. The length of the stretched spring is just going to be 0.3 squared plus 0.4 squared, and that's going to give us a value of 0.5 meters. Now, to find the stretched part, we're going to go back to the L0 here at point A. So L0 we know is 0.4. Sorry, this is L1, the length from this point to point A. And we want to find the unstretched part of the string. Unstretched spring. So that's going to be minus x1. Therefore, L0 is 0.3 meters. Now that we know all of this, we can easily find x2. It's just going to be L2 minus L0 to give us 0.2 meters. Okay, so a little refresher. The formula for kinetic energy is T equals to half mv squared. The formula for gravitational potential energy is V is equal to mgh the elastic potential energy is half kx squared, and the work energy equation is U is equal to difference in D plus difference in V, where V is just the elastic potential energy plus the gravitational potential energy. this formula only works, this formula can be equal to 0, so the work done is 0 only when there are no external forces. So only gravitational, elastic, and non-working constraints. Therefore, if this is 0, it becomes T1 plus V1 is equal to T2 plus V2. Now that we've learned all of this new information, we can start solving. There are no external forces on the problem. It's just gravitational, elastic, and kinetic energy. So you've got delta T plus delta Vg plus delta Ve is going to be equal to 0. And we know the equations for all of those. So we're going to have mv2 squared minus v1 squared plus mgh2 minus h1 plus half k x2 squared minus x1 squared is all equal to 0. h2 is 0. And then we just plug in what we know. Here we're going to add 2. We're going to multiply the elastic potential energy by 2 because there are 2 springs. So this is just for the elastic potential energy. And that's going to finally give us V2 is equal to 2.26 meters per second. Now for question 2. The collar has a mass of 2 kilograms and is attached to a light spring which has a stiffness of 30 newtons per meter and an unstretched length of 1.5 meters. The collar is released from rest at A and slides up the smooth rod under the action of the constant 50 newtons force. What is the potential energy of the spring at time is equal to T0? And then for part B, find the velocity of the collar as it passes by position B. And then for part C, draw a free body diagram of the collar when it is in position B. Okay, what do we know? We know that the mass is 2 kilograms. The stiffness is 30 newtons per meter. The unstretched length is 1.5 meters. And an external force is 15 newtons. We also know that the velocity at A is 0 meters per second. So right here. For part A, we want to know what the elastic potential energy at A is. So T is equal to 0. So from our last problem, we know that to find XA, we have to find the stretched length at A minus the unstretched length. unstretched length. And since we know both here, it's 2 meters, we know that XA is going to be 0.5 meters. Now the elastic potential equation we know is going to be VE is equal to half K XA squared. And if we plug in what we know, we get VEA is equal to 3.75 joules. Okay, now for part B, this one's going to be a little bit tricky. We want to find the velocity at B. So the velocity right here. We're going to start off with the work-energy equation. We know that that's equal to U is equal to delta T plus delta V. The kinetic energy equation is T is equal to half, we know it's half mv squared, but the delta T is also equal to TB minus TA. And since VA is equal to 0, then the kinetic energy at A is also 0. Therefore, delta T is only the kinetic energy at B, which is half mvb squared. Now for the potential energy, it's going to be delta V is equal to VB plus VGB minus VEA minus VGA. Now, the gravitational potential energy at A is equal to 0 because HA is 0. Here, we're assuming this is where the y-axis starts, so the height is 0 at A. Therefore, delta V is going to be equal to half kxb squared plus mghb minus BA. Now we want to find xb over here. We're going to go back to what the spring looks like when it's stretched at B. So this distance over here is 1.5 meters. This distance over here is 2 meters. So the stretched length at B is going to be 1.5 squared plus 2 squared under the square root. That's going to give us 2.5 meters. And the stretched part of the spring is just going to be LB minus L naught. And since we now know both, XB is 1 meters. Now we plug in everything we have. To get delta V is 40.68 joules. Okay, now for the work equation. We know that work is force multiplied by distance. So, since the force is pointing at an angle of 30 degrees, we're going to have to equal it to 4F multiplied by HB minus HA, which is 0, cosine 30, because we want to know the force component in the y direction. If we plug in our known values, we can get 64.95 joules. Now we plug everything into the main equation again. This one, we're going to get 64.95 is equal to half 2 VB squared plus 40.68 to finally give us VB is equal to 4.93 meters per second. And for part C, where it's asking for a free body diagram at position B, we're gonna draw the collar here. Sorry, let me draw this a little bit bigger. This is our collar. This is the weight pointing down. Our spring is going to be pulling it that way. So this is the force due to the spring, which is equal to stiffness multiplied by distance. This is our y and x coordinates. Gravity is pointing that way. The normal force is going to be pointing this way. And the external force, pulling the collar up, is going to be pointing this way. Okay, so for our last question of the tutorial, we've got here a system that is released from rest with a spring initially stretched at 25 millimeters. Calculate the velocity v of the 60 kilogram cart after it has moved 100 millimeters down the incline. Also, determine the maximum distance d traveled by the cart before it stops momentarily. Neglect the mass and friction of the pulleys and wheels. Now, for this question, it's going to be a little bit more challenging than the previous two questions, so it's especially important to write down our known variables. Just to get familiar with the question and what it really requires. So in the beginning, so step 1, at t is equal to 0, we've got x1 is 25 millimeters, and v1 is 0 meters per second. Now step 2, at d2, we've got d2 is 100 millimeters, the cart moving down the incline, and we're trying to find what v2 is. And then step 3, at v3 is equal to 0, when the cart stops, we know that v3 is 0 meters per second, and we want to know what d3 is, how far it went down the incline. Okay, so now we can start. Okay, now we can start. So we know that from 1 to 2, that's where we're going to start our analysis. We're going to write down our work energy equation. which is U is equal to delta T plus delta V. This is going to be equal to 0 because there is no external force. So 0 is equal to half mv2 squared minus v1 squared plus half kx2 squared minus x1 squared minus mg h2 minus h1. So this is negative here because it's going down, the card is going down. And v1 we know is equal to 0, and h1 is also equal to 0. Now if we want to calculate what h2 is equal to, we're going to need to calculate the incline. So we've got an angle of 20 degrees here, and we want to find how far it went down after it traveled the distance of d2, which is 100 millimeters. We want to know what that translates to into height. So that's going to be equal to d2 sine 20, which gives us 0.0342 meters. Now to find what x2 is equal to, it's going to be a little bit complicated. We're going to find first the constrained motion of connected particles equation. Or other words, the Pauli cable equation. So if we go back here, we have 3 cables of equal length. I mean, it's one cable, but you know, they're all equal length. So that's going to be 3s is a constant. That's the length of the cable. Therefore, the additional stretch in the spring, so however much it stretches in this direction, runs at 3 times the additional distance traveled by the cart. So 3 times this distance over here. Okay? Because of this over here. So the additional stretch in the spring runs at 3 times the additional distance traveled by the cart. Or in other words, 3d2 plus x1 is equal to x2. Now once we plug that in, our known variables, we're going to have 0.325 meters is equal to x2. Now we're going to plug in all of our known variables in the big equation over here. To finally get V2 is equal to 0.382 meters per second. Now we still have D3 to figure out. So now we're going to start analyzing from 1 to 3, the final step of our problem. So as usual, the work energy equation is going to be from 1 to 3. the work done from 1 to 3 is equal to delta T plus delta V is equal to 0. And this is also equal to 0 because V1 and V3 are both equal to 0. So we're just going to be analyzing the potential energies. So 0 is equal to half K x3 squared minus x1 squared minus mg h3 minus h squared minus h1, and this is going to be equal to 0. If you want to find the stretched part of the spring at 3, it's going to be, as we figured out here, 3d3 plus x1. And if you plug that back in into our equation, it's going to give us a hideously long quadratic equation, something along those lines. This part is A, this part is B, this part is C. And we're going to plug it in into the quadratic equation. D3 will be equal to minus B plus or minus B squared plus 4AC over 2A. And that will give us a final answer of D3 is equal to 0.1325 meters or 132.5 millimeters. And that's the end of our questions. Thank you so much for watching this video. If you have any questions, leave it in the comments below or email me on noor.doedar@mail.tutorana.ca. Thanks and see you next week.